So in today's video, we're going to look at Newton's law of cooling. Now, Newton's law of cooling is another application of first-order ordinary differential equations. So the notation is as follows. We have T, which is T of t, which is the temperature at a time t. And we have T sub a, which is the temperature of the ambient space around said object. So our differential equation looks like dt dt, so d of the temperature with respect to time, is equal to negative constant times the temperature minus the ambient temperature, where K is always positive. So what this formula says, what Newton's law of cooling says, it's saying that the change in temperature with respect to time is equal to some constant times the difference in the temperature of the object minus the temperature around the object. So we can model it with, so using this equation and using our knowledge of first order ordinary differential equations, we can solve for the time that it will take for an object to cool down or for an object to heat up. So to show this, let's look at the first example. So in the first example, we have a body is heated to 110 degrees Celsius and placed in air at 10 degrees Celsius. After 1 hour, its temperature is 60 degrees Celsius. How much additional time is required for it to cool to 30 degrees Celsius? And it gives us the answer. So for this problem, we have a body heated to 110 degrees Celsius. Well, first of all, let's look at units. So our time is in hours, and our temperature is in degrees Celsius. So now our first condition, we're given our body is heated to 110. So that at time 0, this is where it's starting, is 110. Our ambient temperature is 10 degrees. After 1 hour, its temperature is 60 degrees. So our second condition at 1 hour is 60 degrees Celsius. How much additional time is required for it to cool to 30 degrees Celsius? And that's our third one. So it wants to know how long, which will be lowercase t, is required for it to cool to 30 degrees. So we're solving for t, lowercase t. So let's write out our differential equation for Newton's law of cooling. So we have dt is equal to negative K times the temperature minus the ambient, which in this case is 10. Now, looking at this, we should be able to immediately tell that this is a separable equation, right? We can divide both sides by t minus 10. And that's equal to Newton minus K dt, right? Integrate both sides. Natural log t minus 10 is equal to negative kt plus c. We want to get rid of that pesky natural log over there. Let's take the exponential both sides. T minus 10 is equal to that c comes out, multiplies by the whole thing. E to the negative kt. Now, let me just explain why that is, just in case some people haven't watched the first few videos. So we have, this would become e to the minus kt plus c. Excuse me. This can be rewritten as, right? This right here becomes a new constant, and I just called it c again. You can call it anything you want, p, m, n, whatever. Doesn't matter. You need a new constant though, so that's why the c comes out front. That's where that little c comes from here. C e to the minus kt. So now that we're here, we can simplify this a little bit. And now we have our first equation here, where we have t of 0, we use our first condition, is equal to 110. So now we have this. We want to use it to solve for c first. We're going to solve for c first, okay? So in this case, our time is 0, and our temperature is 110. So 10 plus CE, time is 0. This is just 1. C is equal to 110 minus 10, right? 100, so C is equal to 100. We plug that back in and we get our second equation. T is equal to 10 plus 100 e to the minus kt, where t of 1 is equal to 60. So now our temperature is 60 and our time is 1, so that's just negative k. 60 minus 10 is 50. 50 over 100 is 1/2. Take the natural, we want to get rid of the e now, so we have to take the natural log of both sides. Now that we did that, the natural log of 1/2 can simplify to negative ln of 2, which is equal to negative k. Negatives cancel. K is equal to the natural log of 2. Yep. So now we plug this back in and we get equation 3. So now in equation 3 we have t is equal to 10 plus 100 e to the minus ln of 2 times t, where we have our last condition, t of lowercase t is equal to 10, right? 10? Nope, 30. So we're going to find out what time, how long it takes for it to be 30 degrees, how long it took for it to cool to 30 degrees. So, well, what am I doing? This should be down here. Right? So now we have temperature is 30. Time is t. And we need to solve for t now. So this would be 20, right? 30 minus 10 is 20, is equal to 100 plus e to the minus ln of 2 times t. 200, oh wait, that's 100 times, sorry. 200 divided by 100, that becomes 2 over 10, which becomes 1/5. Which is equal to e to the negative ln 2. So this looks similar to what we had before. We have to take the natural log of both sides, right? To get rid of the e. The left side can simplify like before. This is negative natural log of 5 is equal to negative natural log of 2 times t. So then t, negatives cancel, ln of 5 over natural log 2. And if we look back up here, the answer was natural log 5 over natural log 2. Perfect. If you have any questions, you can leave a comment on the video. I will respond pretty much immediately. So now let's look at the next question. This one's a little more tricky. This one, when I was in the class, when I was working on this stuff, This one got me. I'm not going to lie. This one was a little tricky because you have to kind of work backwards for this one. And you'll see why in 1 second. So let me read it. A package of meat of unknown temperature is placed in a freezer, which is kept at a constant temperature of 0 degrees Fahrenheit. Right off the bat, let me write that down. So we know that our ambient temperature is 0. After 15 minutes, temperature is 30 degrees. And after 30 minutes, it is 15 degrees. What was the initial temperature of, excuse me, what was the initial temperature of the meat? So let me write that like this. The initial temperature is at time 0. And I'll just call the initial temperature T naught, I guess. Yeah, I'll call it T naught. So for this one, if you look at the last question, it wanted how much time is it required for it to cool down to a temperature. So I started at a high temperature, and I want to know the time to take for it to cool down to a lower temperature, right? For this one, we start at, we don't know. We start at an unknown temperature. All it gives us is the temperature of the package at 15 minutes and 30 minutes. So we know it has to be warmer than 30, obviously, right? It has to be warmer than 30. So let's find the initial temperature of the meat. So for this one, instead of going 1, 2, 3, right? We're not going to do that. We're going to go backwards. 1, 2, 3. And that's what got me when I first did this problem. This is what I was having a hard time with. Because you have to start with what's given to you first, basically. It tells you what happens first. It tells you what happens second. But then it wants to know what the initial temperature is. And you'll see how it works out. But for me, it's really hard to understand like why you have to go in this order until you fully solve out the problem, and then you'll see why we had to do it. So I'm just going to go ahead and go through it, and I'll explain as I go. So let's write our equation out. See this one, very nice. Our ambient temperature is 0. So this is just times T minus 0. So that's dt over T is equal to minus K dt. That's the natural log of T is equal to, oh right, because I integrated both sides, negative K T plus C. Take the, exponentiate both sides, that says T is equal to C e to the minus KT. This is our first equation, where we have T of 15 is equal to 30. Let me just make sure I'm not making any mistakes here. Yep, that's right. Okay, so now our temperature is 30 and our time is 15. So just like the last one, we solve for the constant that's out front first, right? So we're going to solve for C first. This is another thing that I had a hard time with. I'm pretty sure I remember I was like solving for K first or something. It might work out the same. I'm honestly not too sure about that. But just to be safe, think of it as you always solve for the constant that's out front first. So C is equal to 30 over e to the minus K times 15. Right? I think. Okay, so I just noticed a mistake in my initial order of my conditions here. So let me think about this. After 15 minutes, the temperature is 30, and after 30, it is 15. What's the initial temperature of the meat? Okay, so, yeah, it got me again. So for this one, this is a weird order. I know. We're gonna start with that one first. Yes, that's right. Okay, now I remember. You start with the highest temperature. You start with the highest time first, and you have to work. Like I can't go from 15 to 30 to 0, right? That made no sense. What I was doing before, you can't go from 15 minutes to 30 and then back to 0. You have to go from 30 to 15 down to 0. You have to go down like that. Sorry, that's my fault. I was thinking it in terms of temperature, not time. You have to think of it in terms of time. So you can either go backwards or forwards. So you have to go time 30, then time 15, then time 0. So let me fix this. This would be time, start with time 30 is equal to 15. So then 15 is equal to negative k times 30. So I'll rewrite that. So this is 15 over e to the negative 30k. Yeah, that makes a lot more sense. Sorry about if I confused anyone. So now I guess we can solve, well, we can plug c back in. So we have t is equal to 15 over e to the negative 30 times k times e to the, is that e to, wait, oh yeah, e to the minus kt, right? Yep, and this is our second one, I think. Yep. So then we have t of 15 is equal to 30. So then we have 30 is equal to 15 over e to the minus 30 times k times e to the minus 15k. So this can simplify. E to the minus 15k over e to the minus 30k will become e to the minus 15k, right? So then I guess we can solve for k, yeah. So then k would be, let's see, e to the minus 15k is equal to 15 over 30. 15 over 30 is 1/2. So then take the natural log of both sides. Negative 15k is equal to the natural log of 1/2. This becomes, well, I can keep it like that for now, actually. K is equal to negative the natural log of 1/2 over 15. So now we can plug k back in. So let me look back up there. T is equal to 15 over e to the minus 30 times negative natural log 1/2 over 15 times e to the minus natural log 1/2 over 15 times t. And we have one final condition, right? Where t of 0 is equal to t naught. Okay, so trying to think of how I can simplify this first term. 30 over 15 is 1/2. So that's just t is equal to 15 over And those negatives will cancel. So then that's just 1/2 ln of 1/2. Times. Okay, let me plug in my condition here. Sorry, so that's T naught is equal to E. This would just be 0. So this is 1. So then we're left with T naught is equal to 15. So this is our answer right here, actually. So if I plug this, let me get my calculator. So if I plug this into my calculator, so we have E, where's E? There's E to the 15 over 1/2 natural log of 1/2. We have, something's not right here. Hold on. What did I do wrong? Oh, 30 over 15 is not 1/2, it's 2. Which you can actually rewrite this then as, let me write it like this. This would become negative 2 ln of 2. So let me put that into the calculator. Sorry about that. Keep making mistakes here. 15 over 2 natural log of 2. Oh, negative 2 natural log of 2. Negative 2 natural log of 2. And I get, still not getting the right answer. 30 over 15 is 2, right? Yeah, 30 over 15 is 2. It's negative. I have a sign error somewhere. Let's look. Oh. No, that becomes positive. Oh my god. I see what I did. I was putting it in the calculator wrong. So it's 15 over that whole thing. I thought it was e to the 15 over. Yeah, it's 15 over e to the 2 ln of 1/2. Oh, geez. So that is then equal to... I was right. I did not have sign error. E to the negative 2 natural log of 2, which is 60. Yeah, that's the right answer. 60 degrees. So let's do a little recap here. So they wanted us to find the initial temperature of the meat because it wasn't given to us. So you can even see, like, at 15 minutes we know the temperature, at 30 minutes we need the temperature. We can actually use Newton's law of cooling to go back and find the initial temperature, which is really cool. I think it's really cool that we can do that, stuff like that. That even if we don't have like the data for it, we can still figure it out with Newton's law of cooling. So yeah, but remember, always start with the initial time. If we're finding initial time, we start with the highest temp. We start with the last time, so that's 30 minutes, and we go down to 0. So that's why we did 1, 2, and then 3. For this one, it was pretty straightforward. It wanted us to know what the time it took to cool to 30. So then it would be 0, and then after 1, and then that time. So it's pretty straightforward. So yep, that's Newton's law of cooling.